the problem is given like this. A steel ball whose specific heat Cp is 0.46 kilojoule per kg degree Celsius and conductivity K is 35 watts per meter degree centigrade, 5 centimeters in diameter, and initially at a uniform temperature of 450 degrees centigrade is suddenly placed in a controlled environment in which the temperature is maintained at 100 degrees centigrade. The convection heat transfer coefficient is 10 watts per meter square degree centigrade. Calculate the time required for the ball to attain temperature of 150 degrees Celsius. Now the solution could be given like this. And here we could anticipate, we could foresee that the lumped heat capacity analysis is valid because the size of the ball is very small, 5 centimeters diameter, and the steel has got very good thermal conductivity. So internal temperature gradients must always be neglected under such cases. And even then we have the criteria of Biot number. First let us calculate what is Biot number. That is Hs by K, H into V by A divided by K. H is given as 10, 4/3 pi r cube, that is volume 0.025 whole cube divided by area is 4 pi r square into K is 35. The result is 0.0023, which is much lesser than 0.1. So hence lumped heat capacity analysis is valid because Biot number is less than 0.1. That is, internal temperature gradients can be neglected. Now let us solve the problem because initial temperature is given as 450 Celsius. Fluid temperature is given as 100 Celsius. The temperature to be reached by the body is given as 150 Celsius. Density is 7800 kg per meter cube. This is the specific gravity of the density is 7.8. H is natural convection heat transfer coefficient 10 watts per meter square Celsius, and specific heat Cp is 460 joule per kg degree centigrade. Therefore, HA by rho V Cp we could calculate as area is 4 pi r square, surface area of the sphere. Density is 7800. Volume is specific heat is 460, volume is 4/3 pi r cube. So HA by rho ECP is 3.44 into 10 power minus 4 per second. Now we got that T minus T infinity divided by Ti minus T infinity, that is Ti is initial temperature before quenching of the body, E is equal to e to the power of minus HA rho VCP into tau. So substituting all the values, we get 150. The temperature to be reached by the body is 150, that is given. Ti is 450 minus 100 is equal to e to the power of minus 3.344 into 10 power minus 4 into tau. So here tau is 5819 seconds, that is 1.62 hours. After 1.62 hours of quenching of the body, the temperature of the body would reach 150 degrees Celsius. That is from 450 degrees Celsius to reach 150 degrees Celsius for the body, it will take 5819 seconds. Hence the problem. Now I shall solve another problem given in GATE 2005. The problem is given like this. A small copper ball, from the data itself we can guess it is a small ball of very high conducting material body, therefore lumped heat capacity analysis is obviously valid, of 5 mm diameter, yet problem of GATE 2005. Yet 500 K is dropped into an oil bath whose temperature is 300 K. The thermal conductivity of copper is 400 watts per meter Kelvin. Its density 9000 kg per meter cube, and its specific heat 385 joule per kg Kelvin. If the heat transfer coefficient is 250 watts per meter square Kelvin and lumped analysis is assumed to be valid, the rate of fall of the temperature of ball at the beginning of cooling will be in Kelvin per second, A 8.7, B 13.9, C 17.3, D 27.7. here he is asking the solution could be given like this. Here the rate of fall of temperature dou T by dou tau at tau is equal to 0 seconds is how much? That is the question that is asked. So writing energy balance equation or first law of thermodynamics, the rate of convective heat transfer from body to fluid is equal to the rate of change of internal energy of body, that is at tau is equal to 0 seconds at the moment when the body is quenched, HA T initial temperature minus T infinity is equal to minus d by d tau of MCP T at tau is equal to 0 seconds. Because I had written TI left hand side, it means initially at tau is equal to 0 seconds the body has got an initial temperature of Ti. Here Ti is given as 500 K, T infinity is 300 K, mass is equal to volume into density, that is 4/3 pi r cube, that is the volume of the ball, into density. We could obtain the mass also in kg. Specific heat is given as 385 joule per kg Kelvin. H is given as 250 watts per meter square Kelvin. It is an oil bath. Slightly higher values of H are found because it is liquid. Convection with liquid, higher values of H are expected. Therefore, substituting 250 into 4 pi r square into 500 minus 300 is equal to minus density into 4/3 pi r cube into specific heat into dt by d tau at tau is equal to 0 seconds, from which dt by d tau, the rate of fall of temperature, the dt by d tau at tau is equal to 0 seconds, could be calculated in Kelvin per second. Hence the answer could be obtained. Hence the problem. In this problem, the lumped heat capacity analysis is already valid, that is given in the problem. So Biot number don't have to be checked. Even if you check the Biot number from Hs by K, the where S is given by volume by surface area, we would be definitely obtaining a Biot number value of less than, Biot number value of less than, much lesser than 0.1, which is the criteria for lumped heat capacity analysis. So at the moment the body is quenched, what is the rate of fall of temperature we had calculated. In fact, as the time passes, the rate of fall of temperature with respect to time, that itself will be decreasing, because the temperature difference between the body and the fluid or the oil bath is decreasing. The rate of fall of temperature with respect to time, as the time progresses, will be decreasing. It will not be as high as at the initial cases, that is at the tau is equal to 0 seconds. Now I shall solve a problem in GATE 2006. The problem is given like this. In a composite slab, the temperature at the interface between two materials is equal to the average of the temperatures at the ends. Assuming steady state one-dimensional heat conduction, which of the following statements is true about the respective thermal conductivities? The figure is given along with the problem like this. This is T interface, T1, T2. This is 2B. This is B. This is conductivity K1 for the slab 1, conductivity K2. The solutions are given like this. A, 2K1 plus K2. 2K1 is equal to K2. B, K1 is equal to K2. C, 2K1 is equal to 3K2. D, K1 is equal to 2K2. Now it is a steady state one-dimensional heat conduction. Therefore, the current should be same throughout. Since the solution is given like this, since it is series circuit, thermal circuit given like this, T1, T interface, T2. The first resistance is 2B by K1A, where A is the area of heat transfer, which is same throughout. Second resistance is B by K2A, implies Q is equal to T1 minus T interface divided by 2B by K1A is equal to T interface minus T2 divided by B by K2A. So A and A get cancelled. So T interface is given the average of T1 and T2, that is T1 minus T1 plus T2 by 2 divided by 2B by K1 is equal to T1 plus T2 by 2 minus T2 divided by B by K2. B also gets cancelled. It results in 2T1 minus T1 minus T2 divided by 4 is equal to T1 plus T2 minus 2T2 by 4 by K1, divided by 1 by 2 by K2. So it results in T1 minus T2 by 4 by K1 is equal to T1 minus T2 divided by 2 by K2. So implies 4 by K1 is equal to 2 by K2. 4K2 is equal to 2K1. K1 is equal to 2K2. Answer is D. Hence the problem.